In this video, we are going to expand on our limit definition for the slope of a curve and begin to understand that as the derivative. So, looking at this definition, f of x sub 0 plus h minus f of x sub 0 over h, essentially that represents the difference quotient. And you should have learned about this previously in your algebra class. And the difference quotient really is representative of the slope of a secant line. And a secant line is a line that's going to pass through 2 points, right? And we are building towards talking about the slope of a tangent line. So the slope of a line that touches just at 1 point. And I can draw that, make that look a little nicer. It just touches 1 point, a nice straight line. So secant and tangent lines are different. And so when we talked about this slope definition and we add the limit as h, remember h is that horizontal distance between my two x values. We've got x sub 0 and x sub 0 plus h. Okay, so when we look at that, we're considering this as the limit as h approaches 0. Now, h is not allowed to equal 0, but we're looking at making that distance between those 2 points when we calculate our slope infinitely small. Okay, so we said that this guy right here, the limit of that difference quotient as h approaches 0, well, what we're going to learn is that that represents our derivative. The derivative of a function, f, at a point x sub 0 is denoted using this notation with an apostrophe. F prime of x, or x sub 0 in this case. So that reads as f prime of x. So this is my derivative notation. And what is a derivative? Derivative represents a rate of change. The derivative represents the slope at a specific x value. Okay, so the difference quotient of f at this x sub 0 point with an increment, a horizontal space between my two x values, which we call h, as that h value approaches 0, this is called our derivative. So as we move forward in this unit and I ask you to calculate a derivative, you are going to be essentially finding the limit as h approaches 0 of our difference quotient. And f prime of that x value, f prime, is the way we say derivative in calculus. So let's look at an example. In this example, we're going to find the derivative of the function. And the function given, f of x, equals the square root of x. So we want to make sure that we understand our derivative formula. And I'm going to rewrite it here without my x sub 0. We'll just say f prime of x, the derivative of a function. F prime of x means the derivative of that function f. What that's going to be is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So if we are to find the derivative in this case, well, that would represent f prime of x equals the limit as h approaches 0. If I take x plus h and plug that into my function, I end up with the square root of x plus h. And f of x is what's given, so I have minus the square root of x, because that was my original function, all over h. So this is my setup. And of course, in order to calculate this, we want to find the limit as h approaches 0. So ideally, we want to take that 0 and plug it in for h. However, I can't do that yet because I have h in the denominator, which would give me 0 in the denominator or an undefined value. So we need to determine how to manipulate this so that we can plug in 0 for h. Now, in this situation, we're dealing with radicals. We've got these square roots here. Okay, and when we're dealing with square roots and radicals, we have a trick. We're going to multiply by a number, and the way we are allowed to multiply by a number is it's okay to multiply by a value of 1. So anything over itself is going to be equal to 1. When we're dealing with square roots, we form that 1 by looking at the conjugate. So considering my numerator here is square root of x plus h minus x, my conjugate would be the square root of x plus h plus that square root of x. Okay, so conjugate occurred because we had a minus, we changed it to a plus. Now, I'm not allowed to multiply by a random number, but if I put it over itself, now I am multiplying by 1, and it's perfectly legal to multiply by 1. Okay, so we multiply by 1, and we form that 1 value by looking at the conjugate of this rational expression. So now I'm going to FOIL my entire numerator here. All of this is going to be FOILed. We're going to first, outer, inner, last, multiply, making sure we distribute. The denominator, though, this comes with a lot of practice, but we don't generally multiply out the denominator because the goal here is we want to cancel this h. So the only way we can cancel with rational expressions is to cancel common factors. So I leave the denominator in factored form and I FOIL my numerator. So moving forward, this is the limit as h approaches 0, and we're FOILing all of this. So the square root of x plus h times the square root of x plus h, that's the square root of x plus h squared, or just x plus h. My inner and my outer terms, when I do those two multiplications, those are going to be opposite valued terms, so they're going to cancel. And then when I look at multiplying my last two terms, a positive and a negative, that's going to give me negative the square root of x squared, which is essentially just minus x. So my numerator simplifies to that, and my denominator, I have h times the quantity square root of x plus h plus square root of x. All right. Now what we notice is the numerator, I have x minus x, that simplifies out. I have the limit as h goes to 0 of h over h times the quantity square root of x plus h plus square root of x. And you should notice here that I have times h in the numerator, that's h times an invisible 1, and times h in the denominator. So my h's are now allowed to cancel, and this becomes the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now, at this point, if I am to try and evaluate this and plug in 0 for h, I will not get 0 in the denominator. So I'm going to plug 0 in for this 1h value, and this turns now into 1 over the square root of x plus 0 plus the square root of x. And of course, x plus 0 is just x. So I have 1 over the square root of x plus the square root of x, or 1 over, adding those, I get 2 square roots of x. And 1 over 2 square roots of x, that represents our derivative. So my original function f of x equals square root of x. That was my original. And my derivative, f prime of x equals 1 over 2 square roots of x. That is my derivative, and that is our solution here. So to summarize, if we look at this difference quotient, remember this is my difference quotient, if we look at the interpretation for that limit, the limit as this gap between my x's, h, as h approaches 0, what does that represent? We have many interpretations. It represents the slope of the graph at some specific x sub 0 point. It represents the slope of the tangent line. It represents a rate of change. Remember, rate of change is slope. And all of those terms together, that's what we call our derivative, f prime of x. So they all mean the same thing, slope, rate of change, derivative. So I hope that helps you understand what is going on here in this problem. Again, if you have questions, always email me. I'm here to help.